Okay, so now the YouTube is on. So let me go back to the PowerPoint. Okay, so as I was saying, we're looking at this reaction here, the reaction between carbon and oxygen to form carbon dioxide, right? So if you look at things at the microscopic level, at the level of atoms and molecules, the relationship, quantitatively speaking, between the reactants and the products will be that one carbon atom will react with one oxygen molecule, which consists of two oxygen atoms, to form one molecule of carbon dioxide. So there's a straight up one-to-one relationship between all the substances involved in this reaction. Now, if we were to increase the number of atoms, let me get this out. If we were to increase the number of atoms here for carbon to 12, that means correspondingly, we have to increase the number of oxygen molecules to 12 as well. And we have to do the same thing for the carbon dioxide, right? And again, it's going to be a one-to-one ratio between these different molecules and atoms. So if you were to suddenly increase from 1 dozen to Avogadro's number, then you'd have to do the same for the oxygen and the same for the carbon dioxide. All right. And of course, that would represent 1 mole of each. So basically, this reaction here is a one-to-one relationship, not only between the atoms and molecules involved, but you can also express it in terms of the mole relationship. In other words, we can interpret this reaction as saying that 1 mole of carbon atoms will react with 1 mole of oxygen atoms to form 1 mole of carbon dioxide, all right? Now, one thing you need to keep in mind is that even though the number of moles of each of these substances are the same, the masses are not necessarily the same. And in fact, in this particular case, the masses are totally different. So the mass of 1 mole of carbon is this right here, 12.011 grams. The mass of 1 mole of oxygen is 31.9988 grams. And 1 mole of carbon dioxide would be equal to 44.01 grams, all right? Now, one thing I want to highlight here is something that we talked about, I think, in chapter 2. We talked about the conservation of mass law, which says that in any chemical reaction, the mass of the products will be equal to the mass of the reactants, where we can actually see that at work here. Here we have the mass of the carbon dioxide, which is the only product. And here we have on the left side, the masses of the oxygen and the carbon. And you'll notice that when you add this mass to this mass, which would be the total mass of the reactants, that would be equal to the mass of the product. So again, this is showing you that the conservation of mass law works. All right. Okay. So what you'll find is that for one, okay, so they're talking about here for 4 different elements: helium, sulfur, copper, and mercury. And this is basically a picture of all those elements. All right. So let me see what time it is here. Okay, we have 10 more minutes. Okay, before we take a break. All right, so the point being made here is that, as you can see here, for each of these substances here, for mercury, for copper, for sulfur, and helium, it's 1 mole in each case, but the amounts are different in terms of masses, right? But the number of atoms will be the same, because that's the definition of a mole. 1 mole will contain Avogadro's number of atoms, and that is true for sulfur, for copper, for mercury, and for helium, all right? Obviously, 1 mole of sulfur will have a different mass compared to 1 mole of copper, compared to 1 mole of mercury, compared to 1 mole of helium. And we're going to talk about the relationship between moles and mass shortly. In fact, that's what we're going to talk about right now, the molar mass. So the molar mass, by definition, is the mass of 1 mole of a substance. And usually, the molar mass is expressed in units of grams per mole, all right? Now, it turns out that the molar mass is numerically the same as the atomic mass, molecular mass, or formula mass, depending on whether or not you're talking about an element, a molecular compound, or an ionic compound, all right? However, the units of molar mass, as I said before, would be expressed in grams per mole, whereas the units of the atomic mass, molecular mass, and formula mass would be AMU, all right? So numerically, the molar mass is the same as each of these here, but the units would be different. So just to give you some examples, one atom of sodium has a mass of 22.99 AMU, right? So the atomic mass of sodium is 22.99 AMU, but the molar mass of sodium is 22.99 grams per mole. So numerically they're the same, but the units are different. Here's another example. One molecule of carbon dioxide has a molecular mass of 44.01 AMU, all right? But the molar mass of carbon dioxide is 44.01 grams per mole, all right? Here's another example. Now, in terms of potassium chloride, the mass, the formula mass, I should say, of potassium chloride is 74.56 AMU, but the molar mass of potassium chloride is 74.56 grams per mole. So here we see that in each case, the numerical value is the same, but the units are different. All right, molar mass is expressed in grams per mole, but the atomic mass is expressed in AMU, and the same is true for the molecular mass and the formula mass. Okay, so that's basically what molar mass is all about. So basically, we have now established the relationship between three terms: moles, the number of atoms, which would be related to Avogadro's number, and the molar mass, right? And this is basically showing you, as an example, the relationship between moles, the number of sodium atoms, and the molar mass of sodium atoms. So 1 mole of sodium will contain Avogadro's number, 6.022 times 10 to the 23 sodium atoms, and that would be equal to 22.99 grams. So therefore, we can use these relationships to establish certain conversion factors, which we will find useful when it comes to stoichiometric calculations. So we can have, for example, here, showing you the conversion factor, which represents the relationship between the mole of sodium and the mass in grams of sodium. This is the other way of doing it. By flipping this, we get this. Or, well, not or, and we can also establish the relationship between the moles of sodium and the number of atoms of sodium using this relationship, all right? And then, as stated here, preliminary and follow-up calculations may be needed. And this is what we're going to see later on when we do stoichiometric problems, all right? Okay, another thing that we need to talk about in terms of moles is that within 1 mole of a substance, we can determine the number of moles of particular elements just by looking at the formulas and looking at the subscripts of those elements in the formulas, right? So for example, let's take this compound here. I'm not sure what this compound is, but this is a molecular formula, right? And if you have 1 mole of this compound here, then we can determine the moles of carbon, hydrogen, and oxygen present just by using the subscripts. So in this particular compound, 1 mole of this compound will contain 3 moles of carbon atoms, 8 moles of hydrogen atoms, and 3 moles of oxygen atoms, all right? So we can establish the relationship between the moles of a molecule and the moles of the respective atoms that are present within the molecular formula. Here's another example. We saw this compound earlier. 1 mole of ammonium sulfate. Now in this case, you have to take into account this 2 here multiplying everything within the parentheses here. So therefore, 1 mole of ammonium sulfate will contain 2 moles of nitrogen because of this 2 here. 2 times 4, 8 moles of hydrogen, and then here we have 1 mole of sulfur, and here we have 4 moles of oxygen, all right? So those are some other relationships that we can identify from the formula, and again, this is something that will become important when we do certain stoichiometric type calculations. Okay, so here is an example based on what we have covered so far, right? So basically, this is a combination of 4 questions. So what I'm going to do, and I hope you guys have your PowerPoint available, because what I'm going to do is get out of this so that I can actually show you how to solve this problem on a blank PowerPoint slide. So let me get rid of this here. Okay. So let me start with this, and let me bring my version up on another computer. So let me go here. Okay, so. Okay, so the first question says determine the mass of 0.075 moles of a sample of sodium. That's the A part, right? So the way I would do this is, okay, what's going on here? Okay, so basically you're given 0.0750 moles of sodium. That's what you're given. And the question is asking for you to find out or determine the mass in grams of sodium that's equivalent to this value in moles. So the way I would do this is that I would start off with what we're given, 0.0750 moles of sodium. And I would multiply it by the conversion factor, which relates the moles of sodium to the mass in grams of sodium. In other words, the molar mass. So the way I would set this up is that I would put 1 mole of sodium down here as the denominator. And above, I would put the molar mass, the numerical value, which would be 22.99. Of course, this is a number that you would get from your periodic table. And then all you have to do is crunch a number. So 0.0750 times 22.99. And according to my calculations, when rounded off to 3 sig figs, the answer is 1.72 grams of sodium. All right. And that's basically how that is done. So this is the A part. All right. Any questions about this part? Any questions?
I do have a question. Where does
Yes, sir.
Avogadro's number come in?
I'm sorry?
Where does I'm sorry, where does Avogadro's number come into this problem?
Oh, it doesn't. Actually, it comes into the next problem.
Okay.
So let me do that now and you'll see how it works. All right. So
Okay.
in the next problem, they gave you 62.5 grams. Oh, actually, it doesn't come into that problem, actually. It comes into the C part. So let's do the B part first, and then you'll see Avogadro's number comes into play in the C part. So in the case of B, they gave you 62.5 grams of sodium, and they're asking for you to determine the moles of sodium, right? So the way I would set this up is I'd start off with what is given, 62.5 grams of sodium. And again, I would multiply by the appropriate conversion factor. Now, here's the difference between B and A. In the case of B and A, I'm sorry, in the case of A, this is the conversion factor that is used, all right? In the case of B, you're going to use this conversion factor, which is the inverse. And the reason why is because in this case, you're converting from grams to moles. So you need to put the grams of sodium down here to cancel out with the grams of sodium here. So the only unit remaining would be moles of sodium, all right? So when you do the number crunching, what you're gonna do is divide the 62.5 by the 22.99. Whoops, I did something wrong on my calculator. 62.5 divided by 22.99. And according to my calculation, this works out to be equal to 2.72 moles of sodium. All right? And that's basically how that is done. Okay, so let's get to the C part since you asked a question. So in the case of C, they gave you 1.00 times 10 to the 25 sodium atoms. All right. And they're asking for the mass in grams of sodium. All right. So in this case here, you need to do actually a series of 2 conversion factors. You need to convert from sodium atoms to moles of sodium. And for that, you're going to need Avogadro's number. And then you need to convert from moles of sodium to grams of sodium. And for that, you're going to need the molar mass. All right. So the way you'd actually do that, let me do it down here. You're going to start off with what you're given, 1.00 times 10 to the 25 sodium atoms. And I would multiply that by 1 mole of sodium divided by Avogadro's number, which is 6.02 times 10 to the 23 sodium atoms. All right. So this unit will cancel out with this unit. And then the next step is where we're talking about here, where we have to convert from moles to mass in grams, and that's where the molar mass comes in. So because you have mole of sodium here, you would have to put the mole unit down here. That would be 1 mole of sodium down here. And above, you're going to have the molar mass, which is 22.99 grams of sodium. And we work that out. So 1.00 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.99. And according to my calculation, this works out to be equal to, oh, is that right? Let me do this again. I think I did something wrong. 1.00 times 10 to the 25 divided by 6.02 times 10 to the 23 times 22.99. Okay, that's it. So the answer here is 382 grams of sodium. And that's how that is done. All right. Something just occurred to me while I'm talking about this. All right, you know what? Let me stop here and give you guys a break, and we'll come back in the next 10 minutes. All right.
Sounds good. Professor Nicely, I have a dentist appointment that I couldn't cancel or reschedule today at 12. So I hope it's okay if I leave early.
Hold on 1 minute. Well, when you say leave early, like what time?
11:50 at the
Oh, you mean leaving? Okay. And hold on. I don't know who I'm talking to.
Amos.
Okay. You're not in my lab, are you?
I am in your lab, and I'm sorry I missed it on Monday. I thought it was at 2:30 for some reason.
No. It's at 2.
Okay.
Well,
I'll be there at the lab though today.
oh, you'll be at the lab today.
Yeah, I will.
Oh, okay, all right. Okay, yeah, all right. I guess that can work. I can work with that.
Okay.
All right.
Sounds good.
Mhm. All right. So in the next 10 minutes.
All right. Thank you.
Okay, I am back. Are you with me?
Yeah, with you.
Okay. All
Yep.
right. So we were in the middle of this example. I think we did up to C, right? So let me see here. Uh, let me get rid of this here. So I'm going to focus now on the D part. And the D part is asking the mass of a single sodium atom. Okay, so what I would do to get the mass of a single sodium atom is take the molar mass, because remember the molar mass is the mass in 1 mole, right? I will take the 22.99 grams per mole, that would be the molar mass, and divide that by the number of atoms in 1 mole, which would be Avogadro's number. So that would be 6.02 times 10 to the 23 atoms per mole, all right? And of course, the mole units will cancel out. So whatever you get would be expressed in grams per atom, which is what the question is asking for. So I'll divide 22.99 divided by 6.02 times 10 to the 23. And according to my calculation, this works out to be equal to 3.82 times 10 to the minus 23 grams. So that's the mass of 1 sodium atom. All right. Okay, any questions about this example? Any questions?
No questions.
No question.
All right, let me get over this now and go back to the PowerPoint for this lecture. Okay, what's going on here? It's not responding. Oh, I hate when this happens. Okay. All right, so the next thing I want to talk about is this concept of mass percent composition. And we can calculate the mass percent composition if we know what the chemical formula of the compound is, right? So let's talk about what we mean by mass percent composition. As stated here, it is basically the number of grams of each element per 100 grams of the compound, right? So that's what we mean by mass percent composition. Another way, well, mathematically speaking, we can express it like this: the mass in grams of that element divided by 100 grams of the compound. Or alternatively, we can take the mass of the element divided by the mass of the compound and multiply that by 100%, and that will give you the percentage of that element in the compound. So those are a couple of ways of determining, and we can easily do that if we know what the formula for the compound is. All right, so for example, if you're asked to find the percentage composition of butane, right? So what you'd have to do first is determine the molar mass of butane. So the molar mass, molar mass of butane which is C4H10, would be equal to 4 times 1.008 grams per mole, 8 grams per mole, plus 10, no, I'm sorry, big mistake. The molar mass of carbon is not 1.008, it's 12.01. So let me correct that. This would be 12.01 grams per mole. And in the case of hydrogen, it's 10 times 1.008 grams per mole, all right? So this part works out to be 48.04 grams per mole. And this part works out to be equal to 10 point, this crap is happening again, 10.08 grams per mole. And I'm sorry about that, folks. Okay, let me do this properly. So this would be 10.08 grams per mole. Okay, I give up. So when you add this up together, you're going to get 48.04 plus 10.8. I'm sorry, 48.04 plus 10.08. Okay, so according to my calculation, this works out to be 58.12 grams per mole. So that's a molar mass, all right? Then to find the percentage of each element, what we do is take the total molar mass of each element and divide it by the molar mass times 100%. So in the case of carbon, that would be 4 times, well, that would be 48.04 grams per mole divided by 58.12 grams per mole times 100%. So 48.04 divided by 58.12 times 100. And I got 82.66%. And we do a similar calculation in the case of hydrogen. So in the case of hydrogen, the total molar mass would be 10.08 grams per mole divided by the same molar mass, which is 58.12 grams per mole. My pen is acting up for some reason. I don't know why. Mole times 100%. I'm sorry about this, folks. I don't know why this keeps happening. So 10.08 divided by 58.12 times 100. And according to my calculation, this will be equal to 17.34%. And of course, if you understand anything about percentages, you should know that when you add these two percentage values, that should give 100%. So you can do that as a kind of check to make sure that you're doing the right thing. And it does equal to 100%. So that's basically how that is done. All right. Okay. Any questions about this? Any questions? Any questions?
No questions.
No questions.
All right. So let's see if we can do these questions. It says calculate to 4 significant figures the mass percent of each element in ammonium nitrate. So what would be the first thing you would do in order to tackle this problem? Anybody?
Write the formula.
Okay, very good. So what's the formula for ammonium nitrate? In fact, let me get out of this and get a blank. Okay, so what's the formula for ammonium nitrate?
NH4NO3.
Okay, so NH4 NO3. All right, very good. What's the next step?
Figure out the atomic mass unit.
Well, more specifically, figure out the molar mass.
The molar
Right.
mass.
Right.
Okay.
So how would we do that in this case? Well,
I guess I need another example. I'm sorry.
well, you remember what we did? Hold on, let me get out of this here. You remember what we did here? Let me circle the part that's important. Right here. You remember how we did that?
Yeah.
Okay, so it's basically the same thing.
Okay.
Different compound, but the same process. So let's go back to this here. Okay. So how would you determine the molar mass of this compound?
So what you do is, so N has a has an AMU of
Yeah, you have to consult the periodic table.
Yeah. So the atomic mass of nitrogen is 14.0067.
Okay, let's roll it out to 14.07.
Okay.
Okay, but remember now there are two nitrogen atoms here and here. So what does that mean?
So times 2.
Okay, so multiply by 2, right? Okay, and then what? What do you add to that?
And then hydrogen has an atomic mass of 1.008. So times 4.
Times 4, okay. And what else?
And then add to that 15 point.
Well, let's round that off to 16.00.
Okay.
Let me just say that the periodic table that I expect you to use is the one that I provide for you in Canvas, right? I don't know where you're getting those numbers from, but I would prefer that you use the one that I provided. Because I know the one that I provided rounded off all the answers, all the atomic masses to 4 sig figs. Okay, so what do we multiply this by?
By 3.
Okay, times 3. All right, so that's basically how that is done. So let's do that. So 2 times 14.07, oops, 2 times 14.07 plus 4 times 1.008 plus 16.00 times 3. Okay, so according to my calculations, the answer here works out to be 80.17 AMU. And by the way, I just realized something. Strictly speaking, this would be the formula mass, not the molar mass. So let me just write formula mass, all right? Because it's expressed in AMU. Molar mass, you'd have to convert these AMU values to grams per mole. All right, so let's deal with nitrogen. How do we calculate the percentage of nitrogen?
You take the total the total amount of nitrogen grams per mole divided by
So in other words, you take this.
Yeah.
Okay, let me write that down. So 2 times 14.07 AMU. And what do you do with that?
You divide that by 80.17 AMU.
Exactly. 80.17 AMU multiplied by 100%. Okay, so that would be 14.07 times 2 equals that, divided by 80.17. Okay, times 100%. And according to my calculation, this works out to be equal to 35.10%. All right. Okay, what about the percentage of hydrogen? How do we calculate that?
Would we do 1.008 times 4 AMU over
Well, times 4 divided by?
Let me do this math. Times 4. 4.032. That's not right, right?
No, you have to divide by something. I mean, that part is right, but you're not finished. After you multiply 4 times 1.008, I'm sorry, after you multiply 4 times 1.008, then you have to divide by what? What goes down here?
The 80.17, that?
Exactly, 80.17 AMU times 100%. So let me do that. So 4 times 1.008 divided by 80.17 times 100. So according to my calculation, this works out to be equal to 5.029%. And then we're going to do a calculation for oxygen. So how do we calculate that?
That's going to be 3 times 16.
Okay, 3 times 16.00 AMU divided by
80.17.
80.17 AMU times 100%. So let's do that. So that's 3 times 16 gives you 48 divided by 80.17 times 100. So according to my calculations, this works out to be equal to 59.87%. All right. And so these would be the answers. But again, as I suggested earlier, I would check to make sure that these add up to give you 100%. So 35.10 plus 5.029 plus 59.87. So the answer I got when I add these up is basically 100%. In fact, when rounded off to 2 decimal places, it would be 100.00. Okay, so that's basically how that example is done. Now, there's another question being asked on the same page. Let me go back to it. And that question is, how many grams of nitrogen are present in 46.34 grams of ammonium nitrate? So the way I would tackle that problem is I would use the percentage of nitrogen and multiply it by the mass of the total compound, right? So let me get out of this here. Let me go back to this PowerPoint here. So the number I'll be using in this problem would be the percentage that we calculated here, which would be this number right here, right? The 35.10%. So the way I would, hold on. Oh, I can't erase this. Hold on. Okay. So the way I would deal with this is, hold on, why is this happening? Okay. So the way I would deal with this is I would take the mass of the compound, the total mass, which is 46.34 grams, of ammonium nitrate, and I would multiply it by the percentage of nitrogen, I'm sorry, in ammonium nitrate, which, if I recall, is 35.10%. So the way I'd represent that is 35.10 grams of nitrogen for every 100 grams of ammonium nitrate, right? Of course, this would go with this, and then I'll just do the number crunching. So 46.34 times 0.3510. So according to my calculations, this works out to be equal to 16.27 grams of nitrogen present in 46.34 grams of ammonium nitrate. And that's basically how that particular example is done. All right, any questions about this? Any questions?
I have no questions now.
Okay. All right, so let me get out of this and we're going to continue. Let me see how much time we have left before our break. I have to watch this because I've been going over the time. Okay. All right, so let's move on to a discussion of another important concept, which is actually related to what we just discussed, and that is determining the chemical formulas from mass percent composition. So what we were doing before was determining the percent composition from the formulas. What we'll be looking at now is how we do the reverse. In other words, if you're given the mass percent composition data, how would you determine the formula for the particular compound, right? And it turns out that this is a bit more challenging. What we need to do first is use the percentage or the mass of each element to find the moles of each element. Now, if you're given percentage data, basically what that means is that you have to assume that you're working with 100 grams of the substance, because if you assume that, then the percentages would be equal to the mass of each element, right? So that's the first step. Well, actually, that's the first step that you need to actually do. And then, as stated here, we need to determine the moles. And of course, by now, we should know how to do that. Basically, you take the mass and divide it by their respective molar masses. And then after you get the molar masses, or I should say, after you get the moles, then you try to find what we call the empirical formula by finding the smallest whole number ratio of the moles, right? And we do that by dividing right through by the smallest number of the moles, all right? And the best way to show you how to do this is by looking at some examples. So as you can see on your screen, there are two examples, and we're going to work each of them, all right? So again, I'm going to go to my PowerPoint, my blank PowerPoint here. Again, I'm hoping that you guys can follow along if you have the PowerPoints available or at your disposal. Okay, so let me go here. Okay, and let me do this, let me do that. All right, so the question says phenol, which is a general disinfectant, has a composition of 76.57% carbon, 6.43% hydrogen, and 17.00% oxygen by mass. And the question is asking for you to determine the empirical formula. Now, you're going to see this done in different ways in different textbooks. Me, personally, I prefer to take the approach of drawing a table. So this is what I'm going to do. I'm going to draw a table. At the top of the table, I'm going to have the elements: carbon, hydrogen, and oxygen, right? And then I'm just going to make sure that I have the columns established like this. All right. Now the first row in this table will contain the mass of each element. Now, as I said before, if we're given percentage data, then we can assume that these percentage values will be equal to the mass of each element present in 100 grams of the substance. So in the case of carbon, I'm going to put 76.57 grams. In the case of hydrogen, I'm going to put 6.43 grams. And in the case of oxygen, I'm going to put 17.00 grams. All right, so that's the first row. The next step is to determine the moles of each element. And to do that, what we have to do is divide each of these values here by their respective molar masses. So in the case of carbon, it's going to be 76.57 multiplied by 1 mole over 12.01 grams. That's the molar mass, right? In the case of hydrogen, it's 6.43 grams multiplied by 1 mole over 1.008 grams. And then finally, in the case of oxygen, it's going to be 17.00 grams multiplied by 1 mole divided by 16.00 grams, all right? And then you have to work out each of these on your calculator. So let me do that right now. In the case of carbon, it's 76.57 divided by 12.01. And according to my calculations, this works out to be equal to 6.376 moles. All right. In the case of hydrogen, 6.43 divided by 1.008. And according to my calculation, this works out to be equal to 6.379. 6.379 moles. And then in the case of oxygen, it's 17 divided by 16. And that gives, according to my calculations, 1.0, how many sig fig? 4 sig fig. So that's 1.063 moles. All right. Then the next row is where you're going to try to find the simplest ratio. And the way you do that is that you examine each of these numbers and decide which one is the lowest. And that would be this one right here, right? And then you divide it right through by the lowest value, all right? So you're going to divide 6.376 moles by 1.063 moles. Here you're going to divide 6.379 moles divided by 1.063 moles. And then this divided by itself will give you 1, all right? And then you have to work out the others on your calculator. So let me do that here. 6.376 divided by 1.063. So according to my calculation, this works out to be 5.998. In the case of the next one, let me draw this line here to make sure it's separated. Okay, so 6.379 divided by 1.063. And according to my calculations, this works out to be equal to 6.001. Okay, and that is 1, of course. So basically, if you look at these numbers closely, you'll see that 5.998 is approximately 6. We round this off to the nearest integer. 6.001, of course, is approximately 6 as well. So basically, the empirical formula you're going to get by writing down each element, and each of these numbers here that we calculated here, here, and here would be written as subscripts. So you're going to have C6, H6, and then O. And that would be the empirical formula for phenol. All right. Okay, any questions about this example? Any questions? Oh,
question.
yes. Mm-hmm.
Why did you divide all of them on that bottom row? Why did you divide them by
By the
by
1. 1.063?
Yeah.
Because that's the best way to get the simplest ratio between the different elements. Once you get the moles of each element, what you have to do is divide right through by the lowest mole value of all
Okay.
the elements, right? Because the aim of this is to get the simplest ratio. You want to get the simplest ratio between the carbon, the hydrogen, and the oxygen, because that is what goes into the empirical formula.
Okay, I got you. Thank
All
you.
right. Okay. Okay. Any other questions about this? Any other questions? Okay. So the next example is pretty much the same approach, right? Not much difference, right? The data is different, but basically the process will be the same. So let me get rid of this here. So we're talking about this question right here. We're talking about this question right here, all right? So these are the percentages which we're going to use. So let me get out of that. And let me go here. And let me, okay, so again, I'm going to construct my table. You have carbon, you have hydrogen, and you have oxygen. And let me establish my columns here and here. Oops. And okay. Okay, so the first row, of course, would contain your masses. And again, we use the percentages as the masses. So in the case of carbon, that would be 45.27%. I'm sorry, grams. Okay, let me erase that here. That should be grams. So this should be grams. And then in the case of hydrogen, that's 9.50 grams. And in the case of oxygen, that's 45.23 grams, all right? And then if you remember what we did in the previous example, we convert each of these to moles. So for moles, we take the 45.27 grams and multiply by 1 mole over 12.01 grams. In the case of hydrogen, 9.50 grams, multiplied by 1 mole over 1.008 grams. And then in the case of oxygen, you multiply that by 1 mole over 16.00 grams, all right? And then we do our calculation like we did before. So I'm going to take the 45.27 and divide that by the 12.01. And according to my calculation, this works out to be equal to 3.769. And then in the case of hydrogen, 9.50 divided by 1.008. And according to my calculation, that would be 9.42 moles. And then in the case of oxygen, that would be 45. Let me check something here. 45.23 divided by 16. And according to my calculations, this works out to be equal to 2.827. Make sure I'm telling you the right thing. 2.827 moles. All right. And then, as we did in the previous example, we examine each of these numbers and decide which one is the lowest. And that would be this one right here, the 2.827 moles. So basically, you're going to divide right through by 2.827 moles. So in the case of carbon, it's 3.769 moles. divided by 2.827 moles. In the case of hydrogen, it's 9.42 moles divided by 2.827 moles. And this divided by itself would give 1, right? So again, we need to work out this part here, 3.769 divided by 2.827. And whoops, how did that happen? Let me get rid of that. Okay, so now this is interesting because in this case, you're going to get 1.333. And then if I do the same thing for 9.42 divided by 2.827, you're going to get 3.33 here. Okay, so that's what we get at this stage. And you'll notice that this number here and this number here, they're not exactly close to an integer. So it would not be advisable for us to round it off. So, and another thing you'll notice is that you have a recurring 3 after the decimal point here and here, right? So this is basically, one could see that this is basically the same as 1 and 1/3. And this would be basically 3 and 3 and 1/3 here. So what that seems to suggest is that you multiply in the next step to get the simplest ratio. We multiply by 3. So if you multiply 1.33 by 3, you're going to get 3.999, which is approximately 4. And if you multiply 3.33 by 3, you're going to get 9.99, which is approximately 10. And if you multiply 1 by 3, you're going to get 3 here. So the empirical formula, I'm going to write that up here. The empirical formula in this case would be equal to C4H10O3. All right. So in some instances, when you get to this stage right here, if you end up with a number which is not close to an integer, then in the next step, you need to multiply by a certain integer to convert those numbers into an integer or a number close to an integer so that you can round off to an integer. In this case here, you'd have to multiply by 3, right? In some cases, you'd have to multiply by 2. In some cases, you have to multiply by 4. And, you know, in some cases, it's pretty much a trial and error. You have to figure out what number you multiply by so that you get integers at the very end, which you can use in the empirical formula. Okay, any questions about this example? Any questions? Any questions?
I have no questions though.
All right. All right, so let me get out of this, go back to the lecture notes. Okay, now what we're going to, so what we have done so far in the last 2 examples is that we determined the empirical formula, right? But you could be asked in a question based on the data that is provided to calculate or determine the molecular formula. Now, in order for you to do that, you're going to need some more information. You're going to need some more information to calculate what is known as an integral factor, all right? And then use that integral factor to convert the empirical formula to the molecular formula, all right? Now, of course, we know what the empirical formula is. It gives you the simplest ratio of the atoms of the element present in a compound. And to get from the empirical formula to the molecular formula, you'd have to multiply by the integral factor. So for example, if you have a compound that has the empirical formula CH2, right? Then that means that the molecular formula could be CH2, in which case you multiply CH2 by 1, or it could be C2H4, in which case you multiply CH2 by 2, or it could be C2H6 or C4H8 or C5H10 and so on and so forth, right? So the question is, how do you determine that number? Well, basically what you'd have to do is divide the molecular mass by the empirical mass. Now, the molecular mass is basically the same thing as the molar mass. You can determine that from adding up all the atomic masses of all the elements according to the formula. The empirical formula mass is pretty much the same thing as far as the empirical formula is concerned. In other words, you're going to take the sum of all the atomic masses of the different elements according to the empirical formula. And then basically what you're going to do next is divide the molecular formula mass by the empirical formula mass, and that will give you the integral factor. And then you're going to multiply the empirical formula by that integral factor to get the molecular formula. So here's an example of this type of problem. It says it gives you the empirical formula here, all right? And it gives you also the molecular mass, and the question is asking for the molecular formula. So the way I would do this is, firstly, I would find out what the empirical mass is based on the empirical formula. So the empirical mass would be equal to 3 times 12.01 AMU plus 3 times 1.008 AMU plus 16.00 AMU. So let me do that calculation. So this would be 36.03 plus 3.024 plus 16. So according to my calculations, this works out to be equal to 55.05 AMU. And then what I will do is find the integral factor. I'm going to call it I, right? The integral factor will be equal to the molar mass divided by the empirical mass. So the molar mass is 110 AMU. The empirical mass we just calculated is 55.05 AMU. So when I do that calculation, I end up with 2.0, which is basically 2. So therefore, let me do this up here. The molecular formula would be equal to C3H3O multiplied by 2. So this works out to be equal to C6H6O2. So this would be the molecular formula. All right. Okay, so that's basically how that is done. Any questions about this? Any questions? Any questions?
No, no questions.
All right. Okay. You know what? I'm going to take a break here because this next section deals with a topic which is kind of lengthy, and I don't want to start and stop in the middle of it. So let's take a break, 10 minutes, and then we'll continue with a discussion of elemental analysis.
All right, Mr. Nicely. I think I'm gonna log off now then.
All right.
Yeah. And then but thank you, and I'll see you at 2.
Okay, all right.
All right, thanks.
Mhm. Okay, I'm here. Can you hear me?
Yep.
All right, so it's only you and me for the rest of the time here. All right, so let's talk about elemental analysis. So the previous examples we looked at, we were given the percentage data, and based on that, you're supposed to determine the empirical formula, and of course, in conjunction with the molecular formula, in conjunction with the molar mass or molecular mass, you're asked to determine molecular formula, all right? Now, you might be wondering, how do we get those kind of data? Well, this is what elemental analysis is all about. So, okay, why is this thing not budging? Okay, something is going wrong. Okay, let me go back to here. Okay, so how do we carry out this elemental analysis, which allows us to determine the percentage data? All right. Now, let me just say that the method that I'm about to describe here is one that works for simple organic compounds that contains carbon and hydrogen and oxygen and maybe some other elements. All right. So basically what happens is that the organic compound is burned in oxygen. In other words, we're talking about a combustion reaction. And therefore, the products of that reaction will be carbon dioxide and water. So therefore, what you can do is, if you can find some method of isolating the carbon dioxide and water and weigh them, then you can work backwards to determine how much carbon and hydrogen are present in the original compound. And if there are other elements, you can determine the amount of those elements based on the original mass of the compound. So that's basically an overview of what is done in this sort of analysis. Now, the next slide is going to show you a diagram which basically shows you how this is done. So this basically consists of 3 compartments, all right? The first compartment is the furnace, where your sample, your unknown sample, is heated, right? So this is the compound that you're trying to find the empirical formula for. And while it is heated, oxygen is forced into it so that this compound is completely burnt, right, to form carbon dioxide and water. So if the combustion is complete here, then basically you should have carbon dioxide and water emerging from here and moving into the next compartment. Now, the next compartment contains a substance which can absorb water. In this case, it's magnesium perchlorate. And I think there's another substance that can be used alternatively. I don't remember what it is. But in any case, what will happen is that this substance, the magnesium perchlorate, will absorb the water that is emerging from the furnace. Now, the key thing that you need to do is to ensure that you have enough of the magnesium perchlorate here, all right? So that is important so that it absorbs all the water that is produced. Then after that, the only gas that should be emerging from here would be the carbon dioxide, and that will be led into the next compartment, which contains, in this case, sodium hydroxide, and potassium hydroxide could be used just as well for this purpose. And what happens here, of course, is that the sodium hydroxide will absorb the carbon dioxide, all right? And what you're going to do next is weigh to determine the increase in mass of both the magnesium perchlorate and the sodium hydroxide, right? So the increase in mass of the magnesium perchlorate will give you the mass of the water that is absorbed by it. And similarly, the increase in mass of the sodium hydroxide would be equal to the mass of carbon dioxide that is absorbed by it, all right? And then based on those masses, you can determine the mass of hydrogen and carbon in the original compound, and also you can determine the mass of oxygen if it is present, as well as other elements, all right? So that's basically how this works. Now, let me skip all this here. So here is a simple example of the combustion that would take place between, in this case, methanol reacting with oxygen. And this is the balance equation here. So therefore, if you know the mass of carbon in the carbon dioxide, you can determine the mass of carbon in the original compound. And the same is true for the hydrogen. If you can determine the mass of hydrogen in the water that is produced, you can determine the mass of hydrogen in the original compound, all right? Now, of course, the oxygen will be in excess, so therefore, after some of the oxygen reacts with the carbon, with the organic compound to form carbon dioxide and water, then you're going to have some unreacted oxygen remaining. Okay, so the best way to show you how the calculation is done in this sort of experiment is by going directly into an example, all right? So this is the example that we'll be looking at in this topic. So the question says, burning a 0.100 gram sample of a carbon, hydrogen, and oxygen compound in oxygen yields 0.1953 grams of carbon dioxide and 0.1000 grams of water. A separate experiment shows that the molecular mass of the compound is 90 AMU. So it says determine A, the mass percent composition, B, the empirical formula, and C, the molecular formula of this compound, all right? So let me warn you that the solution for this problem is pretty long. So what I'm going to do is get out of this here. And as I said before, you should follow what I'm doing by downloading the PowerPoint from Canvas. Okay, so let me get that out of the way. Let me get this out of the way as well. Okay, so let me start here. So the question says that you're starting off with a 0.100 gram sample of the compound, and it produces 0.1953 grams of carbon dioxide and 0.100 grams of water. So the first thing I'm going to do is I'm going to start off with the mass of carbon dioxide, 0.1953 grams of carbon dioxide. And what I'm going to do is try to find the mass in grams of carbon present in that carbon dioxide. Because once we find that mass, that would be equal to the mass of carbon in the original compound, because when you're burning the compound, all the carbon in that compound will be converted to carbon dioxide. So how do we do this? Well, we start off with the 0.1953 grams of CO2. And I'm going to convert that to moles. So I'm going to have 1 mole of CO2 above, and the molar mass of CO2, which will be 44.01 grams of CO2 below. All right, and then I'm going to find out the moles of carbon. And based on the formula, 1 mole of carbon dioxide will contain 1 mole of carbon. All right, and then the last step in this process is to determine the mass of carbon, and that would be 1 mole of carbon down here, and the mass of carbon, which is 12.01 grams of carbon. And I would work that out. So 0.1953 divided by 44.01 times 12.01. And according to my is this right? Let me do this again. 0.1953 divided by 44.01 times 12.01. Okay, so that is right. Okay, so the mass I got here is 0.05330 grams of carbon, all right? And then the next step is I will use the mass of hydrogen, the mass of water, which is 0.100 grams of H2O, and figure out the mass in grams of hydrogen present. Again, once you find the mass of hydrogen present, that would be equal to the mass of hydrogen in the original compound. So I'm going to start with the 0.100 grams of water. I will convert that to moles. So that means I would multiply by 1 mole of H2O and divide that by the molar mass of water, which will be 18.02 grams of H2O. And then now, and this is where students tend to make a huge error. The next step is to convert from moles of water to moles of hydrogen. And the conversion factor you use for that is that you're going to have 1 mole of H2O down here, And up here, you're going to have 2 moles of hydrogen, all right? And the reason why you have 2 moles of hydrogen here is because you have a subscript of 2 in the formula for hydrogen in the formula for water. And then the next step, the final step in this process, is to determine the grams of hydrogen. So that means you're going to multiply by the molar mass, which is 1.008 grams of hydrogen over 1 mole of hydrogen. And we work that out. So that's 0.1000 divided by 18.02 times 2 times 1.008. And according to my calculations, this works out to be 0.01118 grams of hydrogen. All right. Okay. So far we have calculated the mass of carbon and the mass of hydrogen. But if you remember, going back to the question, let me go back to the PowerPoint here. The question says that the compound contains carbon, hydrogen, and oxygen, right? So we know what the mass of carbon is. We know what the mass of hydrogen is. So the question is, what would be the mass of oxygen? And to get the mass of oxygen, what we need to do is add the masses of the carbon and hydrogen together and subtract it from the original mass of the compound, which is 0.1000 grams. So let me do that here to get the mass of oxygen. So the mass of oxygen will be equal to the original mass of the compound, which is 0.1000 grams, minus the sum of these two numbers that we just calculated, this number and this number. So minus 0.05330 grams plus 0.01. Oh, by the way, correction, this should be 0.1119. So 0.1119 grams for the hydrogen. So let's work this out. So 0.05330 plus 0.01119, and then we subtract that from 0.100. Oh shoot. Okay, let me do this again. 0.05330 plus 0.01119. Subtract from that 0.1. Okay, so according to my calculation, this works out to be equal to 0.03551. All right. So the question is asking for the percentage of each element. So the percentage of carbon would be 0.05330 grams divided by the total mass, which is 0.1000 grams times 100%. And that would be equal to 1, 2, 1, 2, 3. That would be equal to 53.30%. And then we do the same thing for hydrogen. Percent hydrogen would be equal to, let me see, 0.01119 grams divided by 0.1000 grams. So that would be 11.19%. And then finally, let me see if I can squeeze it down here. Percent of oxygen would be equal to the mass of the oxygen calculated, which is 0.3551 grams divided by 0.1000 grams times 100%. And that would be equal to 35.51%. And that's basically how we answer the A part of the question. All right. And again, I would always advise you to check to make sure that the percentages add up to 100%. Let me check that for myself. 53.30 plus 11.19 plus 35.51. Okay, so yes, it works out to 100%. All right. Okay, so believe it or not, that's the A part. So for the B part, you're going to need the percentages of the elements that we just calculated. I'm just making a record of the percentages for my own. Okay, so let's do that on the next slide. So basically what the question is asking for is the empirical formula. So we have the percentages. That's what we're going to use in the next part. So again, I like to construct a table to do this. That's my preferred method of doing it. So let me do that here. And the first row, as always, will contain the mass in grams, which would be the same as the percentage numbers, because we're assuming that we are working with the mass in grams per 100 grams of the substance. So okay, so for the mass of carbon, that would be 53.30 grams. For hydrogen, that would be 11.19 grams. For oxygen, that would be 35.51 grams. And then we convert these to moles. So if you remember what we did the last time, to convert to moles, we divide each of them by their respective molar masses. 1 mole over 12.01 grams. In the case of hydrogen, 11.19 grams multiplied by 1 mole over 1.008 grams. And then finally, in the case of oxygen, whoops, we multiply this by 1 mole over 16.00 grams. And then we do our number crunching. So 53.30, we divide that by 12.01. And according to my calculation, this works out to be equal to 4.438. Hold on. Yes, 8 moles. In the case of hydrogen, 11.19 divided by 1.008. And according to my calculation, this works out to be equal to 11.10 moles. And then we take the next one, 35.51 divided by 16.00. And according to my calculation, this works out to be equal to 2.219 moles. And then the next step, as we did in previous examples, the next step is to divide right through by the lowest number of moles, which would be, in this case, the 2.219. So here we're going to divide so here we're going to divide by 2.219 moles, right? So we divide, in this case, 4.438 moles by 2.219 moles. And in the case of hydrogen, 11.10 moles, we divide that by 2.219 moles. So let's see what these give. 4.438 divided by 2.219. So that gives exactly 2, believe it or not. So this gives 2.000, which is equal to 2. And then 11.10 divided by 2.219 gives 5.0 0.002. And this divided by itself will give you 1. So the empirical formula in this case works out to be C2H5O, because this here is approximately 5. So that would be the empirical formula for this particular compound. Let me see here. So that's the B part. Now the C part is asking for the molecular formula. Now you'll notice, let me go back to the PowerPoint here. If you look at the question carefully, you'll see that the question does give you the molecular mass, right? So what we can do is find the empirical mass and divide the molecular mass by the empirical mass to get the integral factor, which you're going to use to multiply the empirical formula by to get the molecular formula. So let me just get rid of this crap right here. Okay, so what we need to do first is find the empirical mass. So remember now, the formula was C2H5O, right? So the molecular formula is equal to C2H5O, which means that the molecular mass would be equal to 2 times 12.01 AMU plus 5 times 1.008 AMU plus oxygen, which is 16.00 AMU. So let me just put parentheses here and here just to make sure everything is straightened out. So this part here will be equal to 24.02 AMU plus 5.040 AMU plus 16. Okay, so this should be 16.00. And all we have to do is add these up, 24.02 plus 5.040 plus 16.00. And according to my calculation, this works out to be equal to 45.06 AMU. So to calculate the integral factor I, that would be equal to 90 AMU divided by 45.06 AMU. And that is basically equal to 2. So that tells me that I made a mistake. I made a mistake at the very beginning. It's a minor mistake, but this and this should be corrected right here. Because this should be the empirical formula. And what we're calculating here would be the empirical mass, all right? So basically the molecular formula, which is what the question is asking for, would be equal to the empirical formula, which is C2H5O multiplied by 2. So the final answer is going to be C4H10O2. And that's it. All right. So that would be the C part. So as you can see, it's a bit involved. But if you follow the steps, like I did, making sure that you're careful about your calculations and all that, then you should be able to arrive at the right answer. All right. Okay, any questions about this? Any questions about this example?
No questions. I get the how you did the table. Like I know how to do that step, and how to do the first step, how to get to that point.
Yes, it's pretty straightforward.
Yeah, it is pretty
Um,
straightforward. Just
let,
got
yeah,
practice on it.
yeah, let me just say this, that in some cases, and I think that would be the case in some of the questions in the assignments I'm about to give you. In some cases, you'll be dealing with hydrocarbons, right? Hydrocarbons are basically compounds which contain carbon and hydrogen, right?
Mhm.
In those cases, what you'll find is that this step right here will not be necessary, because if your compound contains only two elements, carbon and hydrogen, that means that there's no need for you to do a calculation for the mass of oxygen. All right? In which case, you only have two elements to concern yourself with, right? So in the table that you would construct, your table would only contain a column for carbon and a column for hydrogen, because there's no oxygen. You see what I'm saying?
I see it.
And basically that's it. It's pretty much the same, process. But the only difference in those instances where you're dealing with hydrocarbons is that you only have carbon and hydrogen to worry about. You don't need to calculate the oxygen, and therefore your table will have only two columns, one for carbon, one for hydrogen, and therefore your empirical formula and molecular formula will only contain carbon and hydrogen. Excuse me.
And in that last step, when you said that we wouldn't need it in the other step, and well, another part of the problem, when you minused it, 2 over, right there, the mass over, when
Right.
the subtraction, the 0.05330 plus the 0.0119, that was what was burned off, right?
Well, hold on 1 minute. Let me see if I get what you're asking. You're talking about this part right here?
Mm-hmm.
Okay. So basically, this here would be the total mass of the compound, right?
Mm-hmm.
The original compound. This here represents the mass of carbon that we calculated in the compound. This here represents the mass of hydrogen that we calculated in the compound, right?
Okay.
So basically, to get the mass of the oxygen, we have to add these two together and subtract it from the original mass of the compound. And that gives us the mass of the oxygen. Because remember, the question said from the outset that there are only three elements: carbon, hydrogen, and oxygen, right? So once you find the mass of the carbon and the hydrogen, all you have to do is add them up, subtract it from the original mass of the compound, and that will give you the mass of the oxygen.
Okay.
All right. Okay, so let me go back to the PowerPoint and see what's the next topic. Okay, let's see here. All right, so the next thing we're going to talk about, again, this is something that you'd have met before in your introductory chemistry, is chemical equations, how to write a balanced chemical equation. All right, so just to briefly describe what happens in a chemical equation, the chemical equation is just basically a shorthand way of representing the changes that is taking place in a reaction. So on the left side of the equation, you'd have the symbol for the substances that are reacting. Those are called the reactants. And then on the right side, you will have the symbols for the substances that are formed, and those are called the products. And in addition to the reactants and products, you might see some other symbols included. For example, you might see what are known as state symbols that are written next to the formulas for the different substances involved. And the state symbols would be in parentheses. S would be for solid, would be for gas, and you have L for liquid and AQ for aqueous solutions, right? Those are the symbols that you'll observe. You may see some other information given, especially above or below the arrow. So let me see if I have, so for example, you might see this, a small triangle or delta, the Greek letter delta, which basically means that you have elevated the temperature in order for the reaction to take place. So in other words, heat is actually applied to the reactant to form the products. In some instances, you might be given more detailed information. So for example, you might be given like an actual number for the temperature, 160 degrees in this particular case, right? And you might be given some other information like whether or not a catalyst was added or the pressure or some other information, all right? So that is usually placed above or below the arrow. Okay, now let's get into the actual important aspect of balancing equations, right? So if you remember, we talked about in the previous chapter, we talked about the conservation of mass law, right? And basically what that law says, just to remind you, is that in any chemical reaction, the total mass of the products will be equal to the total mass of the reactants. And according to Dalton's theory, the reason why that is so is because in any chemical reaction, the number of atoms of each element would be the same in the reactants and in the products, all right? Because basically no atoms would be created nor destroyed as the reaction takes place, right? And that's the thing that the balance equation is supposed to represent. It's supposed to show you that there are no atoms created nor destroyed as you go from the reactants to the products. So let's look at this example right here, the reaction between hydrogen and oxygen to form water, right? So this is the unbalanced equation here, right? We have hydrogen here, H2, we have oxygen, which is O2, and then we have H2O on the right side, all right? Now, if you look at this equation carefully, you'll see that the number of hydrogen atoms on both sides are the same because we have two hydrogens here and we have two hydrogens here, right? But the thing is that the oxygens are not the same on both sides because if you look at this equation here, on the left side, you have two oxygen atoms represented here, but on the right side, you have only one, all right? So basically what that indicates to us is that the equation is not balanced. So the question is, how do we go about balancing this equation? Well, let me show you here what you should not do, right? One thing that you cannot do in order to balance the equation is simply add an element or an atom to one side in order to achieve that balance, as is shown here, right? So if you add an oxygen here, it does balance it, but that's not the correct way of balancing an equation, right? You can't just simply add another atom to the side that needs it in order to achieve that balance. Another thing you cannot do is make any changes to the formulas of these compounds, of any compound. So here is what was done. All the person did here is add a 2 to the formula here for the oxygen. That is incorrect because basically by doing that, you're basically creating a new compound on paper, right? Which of course is not what happens in a chemical reaction. The only changes that you need to make in order to balance an equation is that you need to make changes to the coefficients, right? So if you'll notice here, a coefficient of 2 is placed in front of the H2 here, and a coefficient of 2 is placed in front of the H2O here, right? So now we end up with 4 hydrogens on the same side or on opposite sides of the equation. And here we have 2 oxygens here, and this 2 will multiply the oxygen here. So therefore, the number of oxygen atoms are the same on both sides. And that's basically how we achieve a balance in a chemical equation. And this is a very important skill that you need to master because, as I said before earlier, whenever you're balancing an equation, whenever you're doing any problems involving stoichiometry, you have to start off with a balanced equation. If your equation is not balanced, then more than likely the resulting calculation based on the unbalanced equation would be incorrect. So here I'm just going to show you the guidelines for balancing chemical equations, and then I'm just going to go through a couple of examples. So the first guideline here is that if an element is present in just one compound on each side of the equation, try balancing that element first, all right? The second guideline is that you balance any reactants or products that exist as a free element last. So we're talking about, you know, elements like oxygen, nitrogen, and so on. You try to balance those last. In some reactions, certain groupings of atoms, such as polyatomic ions, remain unchanged. So in those instances, you can treat those groupings as a unit. And then it says here that in some instances, and we're going to see some examples of this, where you can balance the equation by using fractional coefficients. However, those fractional coefficients cannot remain in the final answer, and therefore what you need to do is to clear those coefficients by multiplying by a common factor, all right? So let's look at a couple of examples here. And so let me do the first example. So these are all unbalanced equations, right? So the first example is this right here, right? Iron reacting with oxygen to give you Fe2O3. So the way I would go about this is that first I'll look at the iron here and look at the iron on this side, and I'll notice that there's one iron atom here, two iron atoms on the right side. So I will put a coefficient of 2 here in front of the Fe, right? Now by doing that, well, that's balancing the ions. So the next thing I would do is look at the oxygens, and I'll notice that there are 2 oxygen atoms here and there are 3 here. So the question is, how would you balance oxygens? And what I would do here is that I'll put a fraction here, 3/2. Now you might be wondering, why would I multiply this by 3/2? Because 3/2, which is this here, multiplied by this 2, would give you 3, which balances with the 3 oxygens here. All right. Now, we cannot leave this as the final answer because we need integers as coefficients. So what I would do to this equation, in order to get rid of this fraction here, and more specifically to get rid of this 2 here, is that I would multiply the entire equation by 2. So if I multiply the entire equation by 2, I'm going to get 4 Fe plus 2 times 3/2 will give you 3O2 to give you 2 Fe2O3. So this would be the final answer right here. All right. So that's how that equation is balanced. Let's look at this example right here. So in this example, you have 2 carbons here, you have only 1 here. So I would put a 2 here. All right. And then we have 6 hydrogens here. We have 2 here. So I'll put a 3 here. Now let's get to the oxygens. You'll notice that here that there are 2 oxygens here. Over here, you'll notice that you have a total of 2 times 2, 4, plus 3, 7 oxygens, right? So how do we balance the oxygens? Well, I would multiply this oxygen, O2 here, by 7/2, because 7/2 times 2 gives you 7 oxygens total on the left side, which balances with the 7 oxygens on the right side. Again, we need to get rid of this fraction here. So what I would do here is multiply again the entire equation by 2, and the result would be 2C2H6 plus 14O2. I'm sorry, not 14, 7O2. Let me correct that here. I don't know what I was thinking. Okay, so this would be 7O2, and then on the product side, 4CO2 plus 6H2O. And that would be the balance equation for that question. All right? Okay, so let's look at the last equation. Let's see if you can deal with this one. So how would you go about balancing this equation? Well,
Would we put a 3 in front of the HCN?
okay, let's start off with that. So put a 3 here. And then what?
And then another 3 in front of the NaCN.
Okay, so put a 3 here. Anything else?
I have no clue. It looks good to me.
Yeah, it's balanced. Yes,
It is?
exactly. Yes, it is.
Good.
Right. And what I would suggest you do, when you're balancing equations, after you think you have done it, just do a quick check on both sides to make sure that it's balanced. So like in this case here, you have 3 hydrogens here, you have 3 hydrogens, so the hydrogens are okay. You have 1 phosphorus atom here and 1 phosphorus atom here, so that's okay. You have 4 oxygens here and you have 4 oxygens here, so that's okay. You have 3 sodiums here and 3 sodiums here, so that's okay. You have 3 carbons here, 3 carbons here, and then 3 nitrogens and 3 nitrogens. So now we know that the equation is balanced. All right. Okay. And you're going to have a lot more equations to balance in the assignment that I've posted, or I'm going to post later on today. All right. Okay. Now, there's a reason why it's important for you to know how to balance equations, because based on the balance equation, you can write down what is known as the stoichiometric equivalence between any 2 substances involved, right? Also, it's known as the mole ratio, all right? And that is based on the coefficients of the different substances involved in the balance equation, right? So that's the reason why the equation needs to be balanced before you can establish these mole ratios. So for example, let me go back to my pointer here. Okay, so for example, if you look at this equation here, right? It's balanced already, right? So based on this equation, you can establish mole ratios between any 2 substances involved. For example, the mole ratio between the carbon monoxide and hydrogen would be a 1-to-2 ratio based on their coefficients, right? So therefore, you can write down a conversion factor which represents the mole ratio between the carbon and the hydrogen. So you can write it like this: 1 mole of carbon monoxide divided by 2 moles of hydrogen, or the other way around, all right? And you see similar mole ratios given for other relationships, for example, between the carbon monoxide and the methanol. This is 1 mole ratio. Between the hydrogen and the methanol, that would be another mole ratio. So basically, in order for you to get the correct mole ratio, you need to make sure that the equation is balanced. So that's the reason why you have to know how to balance equations before you can establish the mole ratios. Now, whenever we're doing any calculations involving stoichiometry, basically it comes down to what you see here on the screen. Basically, it's a matter of converting the moles of one substance involved in the reaction to the moles of another substance based on the established mole ratio. Now, more than likely what will happen is that you may need to do some preliminary calculations to get the moles of substance A, and you may also need to do some calculations from the moles of substance A to do, to determine some other values, all right? And we're going to see some examples of this shortly. In fact, here's one example right now. So in this question, they gave you the balanced equation, and the question is asking for the moles of oxygen, and it gives you the moles of propane, which is, well, unfortunately, the question didn't state it, but propane is this compound right here, right? So you're going to take 0.105 moles of C3H8, and you're going to convert that to moles of oxygen. So basically, you're going to write down a mole ratio, which represents the moles of oxygen to the moles of propane, which is a 5-to-1 mole ratio. So we're going to put 5 moles of O2 above, 1 mole of propane below, and then we do our thing on our calculator. So 0.105 times 5 gives you 0.525 moles. Where is this thing? Okay. 0.525 moles, moles of oxygen. So that's a relatively simple example, straight up mole-to-mole relationship, all right? Okay, let me see here, what's next? So a lot of problems would involve this kind of approach, where, for example, you're given, let me get my pointer here. So you may be given the mass of one substance involved in the reaction. You have to convert it to the moles of that substance, and then you use the mole ratio to get the moles of the other substance. And then you may be asked to find the mass of the second substance, right? So it all depends on, the information that's provided in the question. In some cases, you may be asked, based on the information provided, to determine the balanced equation, right? So you could be given the equation expressed as a statement or some words, and then you have to figure out the formulas of the reactants, the formula of the products, and then determine the balanced equation. And then you do the calculation based on any data that is provided. So the best way, of course, to learn and become better at solving problems is by doing a whole lot of practice, such as these problems that you see here on the screen. So I think we'll have enough time to do the first one. The question says the final step in the production of nitric acid involves the reaction of nitrogen dioxide with water, and it says nitrogen monoxide is also produced. So the question is asking how many grams of nitric acid are produced for every 100 grams of nitrogen dioxide that reacts, all right? So what I'm going to do is open up, well, go back to this PowerPoint here, and let me get rid of all this here. Okay, so if you read the question carefully in the first part, it actually describes what is involved as reactant and what is involved as the product. So the question says that it involves a reaction of nitrogen dioxide. So let me write down the formula for nitrogen dioxide and water, H2O. All right. And then it says the products would be nitric acid, which is, of course, HNO3, and nitrogen monoxide, which is NO. All right. So that would be the unbalanced equation. So how would you go about balancing it?
We would put a 2 in front of the NO.
Okay, hold on. So a 2 in front of the NO, you mean here?
Yeah, on the right side, yeah.
Well, I'm not sure if that is correct, because if you put a 2 here, the nitrogens would be unbalanced because you have one nitrogen here plus 2, that will be 3. And you have only one nitrogen on the left side. In fact, what I would have done is, instead of putting the 2 here, I would put the 2 here. I'll put a 2 here, because these 2 nitrogens will balance the nitrogens here and here on the right side. And then let me see here. So in terms of the hydrogens, I have 2 hydrogens here. I have 1 here, so I will put a 2 here. And then in the case of oxygens, let me see here. We have 4 plus 1, 5 oxygens. You have 6 plus 1, 7 oxygens. So the oxygens are not balanced. So how do we balance the oxygens? Oh, wait a minute. The nitrogens are not balanced as well. So what I'm going to do is, let me take this out and put a 3 here. And let's see now. So the nitrogens are now balanced. Okay, now this is the balance equation. 3 nitrogens on both sides, 6 plus 1, 7 oxygens on both sides, and 2 hydrogens on both sides. All right. So now the equation is balanced. All right. So we needed to do that. Okay, you know what? I'm going to take a break here because it's almost 50 minutes. So let's stop here and take a 10-minute break. All right.
Okay.
And then we can move on to the rest of this problem here. Okay, so I'll be back shortly. Okay, hello. Can you hear me?
Hello?
Yeah, I just realized that it's now 12:30, and I don't think we'll be able to finish this example in the time that we have left. So what I'm going to do is just basically call it a day, and we'll continue from here next class. But before you leave, let me remind you that you have an assignment that is due today.
Yep, I already did. I just need to take the pictures and send it in.
Yeah, and hold on, let me see here. Let me check something here. Give me 1 minute here. Let me check something here. Come on. Okay, so according to the schedule, there should be a test that is given this week, but I guess I'll have to put it off until okay, so we have to finish what, chapters 1 and 2 so far?
Yeah, 1 and 2.
Okay. Okay, I'm going to make an announcement about that. So look out for that concerning your test and what it will cover. All right.
Okay.
All right. So yeah, that's basically it for now. So we're just going to stop here and continue our discussion on Monday.
Okay.
All right.
Have a good rest of your day and weekend.
Yes, sir. You too.